I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Have you ever wondered where your old smartphone, laptop, or tablet ends up once it stops working? Every year, millions of tons of discarded electronics accumulate as e-waste, creating one of the fastest-growing environmental challenges worldwide. Hidden inside these gadgets are printed circuit boards, PCBs, the tiny powerhouses that make your electronics work. But when tossed aside, these durable yet complex boards become a major headache for recycling efforts. You see, PCBs are made from layers of fiberglass, copper, and epoxy resin, designed to withstand heat and electrical stress. And that's great for performance, but terrible for recycling. Traditional methods often involve burning or using harsh chemicals to recover metals like gold and copper, releasing toxic fumes and hazardous waste in the process. Worse, much of this e-waste is sent to developing countries where informal recycling harms both people and the environment. So, how can we rethink this problem? First up, scientists are developing bio-based and recyclable PCBs. Imagine circuit boards made from natural fibers and biodegradable resins that break down safely instead of ending up in landfills. These alternatives could revolutionize how electronics are designed for the future. Then there's chemical recycling, a clever method where special solvents dissolve epoxy layers, allowing valuable metals and materials to be separated cleanly. Compared to burning, this is far gentler on the planet. Advanced processes like pyrolysis and supercritical fluid extraction take it even further. Pyrolysis uses high temperatures without oxygen to break down PCBs into reusable materials, while supercritical fluids, pressurized liquids, can extract metals efficiently. These techniques not only reduce pollution, but also recover more resources. But perhaps the most exciting breakthrough is the vitrimer-based PCB developed by researchers at the University of Washington. Unlike traditional plastics that degrade, vitrimers form strong chemical bonds that can be reset when heated with mild solvents. The result? 98% of the vitrimer material can be recovered and reused multiple times without losing its performance. Even better, this method works with standard industrial manufacturing, making large-scale adoption possible. Meanwhile, robotics and AI are transforming recycling facilities. Smarter machines can now automatically disassemble and sort PCB materials with incredible precision, increasing the speed and scale of recycling while reducing human exposure to toxic hazards. On policy front, governments are stepping up, promoting stricter regulations and safer recycling practices to combat the dangerous informal recycling industry, particularly in developing regions. And it's not just about industry and government. Consumers play a role too. Proper disposal, taking advantage of e-waste recycling programs, and choosing electronics made with recyclable materials all contribute to solving this global crisis. As the world faces a mounting mountain of e-waste, sustainable PCB recycling technologies and smarter policies are shaping a circular economy where discarded electronics don't pollute, but instead feed the production of new devices. The path ahead isn't without challenges. Scaling these innovations, reducing costs, and establishing global standards are critical next steps. But one thing is clear. With continued innovation and responsible action, we're on track to turn one of our most dangerous waste problems into a sustainable opportunity for the planet. Because the future isn't just about advancing technology. It's about making that technology work for us without leaving a toxic footprint. Thanks for watching. Subscribe, follow, or visit IDSTH.com for more cutting-edge defense and tech insights. See you in the next one.